Hi girls. In this video I'm going to talk to you about volumetric analysis and I'm going to particularly focus on titration question, which is question 1 from the paper. So what I wanted to do first maybe is just look back over the equation that is the fundamental equation for all the volumetric analyses. In this equation, given a balanced formula where n moles of acid and a moles of acid reacts with n b moles of base to form some sort of a product, the relationship between molarity of the acid and the required volume of that acid for this titration to complete, and molarity of base and volume of the base, which is required to again fully complete the neutralization process, together with the number of moles, is given by molarity of acid times volume of acid over number of moles of acid, and that always equals to molarity of base times volume of the base over the number of moles of base. And this is the fundamental formula, and actually it's quite handy because this is literally just the one formula that we have to remember for all of the volumetric analyses, for all the calculations. So I'm going to walk you through solution of 2014 higher level paper question 1, which is again, as I mentioned, titration question. So in this question we're looking at a situation where a batch of washing soda crystals lost some of water, and we had to determine the percentage of the water loss. So that's kind of just an introductory part to the question, but the important information is here. A sample of the crystal was accurately weighed and found to have a mass of 2.5 grams. So this is mass of the sample of the hydrated crystal. Then that sample was dissolved in DI water to make up 250 centimeters cubic of solution, and the number of 25 cubic centimeters portions of that solution was titrated with a previously standardized 0.1 molar hydrochloric acid. So the mean volume of the titer was 21.6, and I'm going to skip all the theory questions, although I will highlight the fact that it's important that you understand how to use chemical equipment effectively. So tools like volumetric flask or a pipette or a burette. You should have a good understanding of the set of steps that need to be taken in order for you to use those tools. And every year asks about the procedure to follow in order to use any of those tools. And if you remember from the mock exam before Easter, one of the questions was talking about the burette. So again, that's something that's definitely going to come up, and it would be useful if you had that. So anyway, in this case I'm going to look at part E and part F of this question. So I'm going to calculate the concentration of sodium carbonate in the original solution in first moles per liter and then grams per liter. So to find the concentration in moles per liter, in other words, I'm looking for the molarity of the solution of sodium carbonate. So I'm going to use my my formula because that's just, it's handy for me. So before I use it, I'm going to write out all the quantities that take part in this reaction. So molarity of acid, we're told that molarity of acid is equal. So we're told that molarity of acid is equal to 0.1 moles per liter. We are told that the volume of acid, or the average volume of acid used for this titration to reach the end point, was 21.6 centimeters cubic. And number of moles of acid that take part in this reaction from a balanced equation, we have 2, n equals to 2. And then a similar way, molarity of the base is in fact the quantity that we're going to try and find. Volume of the base is given in the problem, and that's 25 cubic centimeters. and finally number of moles of base that equals to 1 from the balanced equation. So what I'm trying to solve in this question is I'm trying to solve this for molarity of the base. So before I start putting all the quantities in, I'm going to move this equation around so that my mass of the base is given. So multiplying across by NB and dividing across both sides by VB, I'm going to get that molarity of the base will be given by a formula. Molarity of acid, volume of acid times number of moles of base divided by number of moles of acid by volume of the base. I can substitute the quantities from the problem, all listed over here, to get that molarity of the base is equal to 0.0432 moles per liter. So that would be the molarity question. Again, if I have the quantities that are required for the titration equation, then I shouldn't have any issues with finding any of the quantities in here. It's all simple algebra, moving things around. So then the next part of this question is to find molarity in grams per liter. In order to find find concentration in grams per liter. So in order to find concentration in grams per liter, all I need to do is to find out what is the mass of 0.432 moles of sodium hydroxide. So relative molecular mass of sodium hydroxide RMM will be equal to twice times 23 for sodium plus 12 for carbon plus 3 times 16 for oxygen, which gives me 106. So 0.0432 times 106 equals to 4.58 grams per liter. So for every liter of this solution, I'm expecting to have to dissolve 4.58 grams of sodium hydroxide. So that answers the second part of the question. Then I have to calculate the percentage of water, of crystallization of the crystals in the value of X, the average number of water molecules in this formula. So what I calculated over here is the amount of moles of sodium carbonate which I would expect to find in 1 liter of this solution. I'm not really concerned with water just yet, it's just the sodium carbonate itself. So if in 1 liter I would expect to see 4.58 grams of sodium carbonate, then in 250 cubic centimeters I would expect to find 4.58 over 4 grams of the solution, which is equal to 1.14 grams of sodium carbonate. So again, 250 cubic centimeters contain 1.14 grams of sodium carbonate. However, the problem tells me that the sample that was dissolved in 250 cubic centimeters weighs 2.5 grams. So the difference between the mass of sodium carbonate in that sample and the mass of the sample is the mass of the water. So 2.5 minus 1.14 equals to 1.36 grams. So 250 cubic centimeters contain 1.36 grams, and if I wanted to express this as a percentage, all I need to do is express the mass of water, which is 1.36 over the total mass of the sample, which is 2.5. That is equal to 54%. So this allowed me to find the percentage of water. Now I need to find out what is the what is the number of molecules of water in this case. So in order to calculate that, I realize that the ratio of mass of water in this sample to mass of sodium carbonate has to be the same as the ratio of the relative molecular masses of those two components. So below the line I'm going to write down 106 for sodium carbonate, and above the line I'm going to write down X for number of molecules of water times 18, which is a relative molecular mass of molecule of water, and that's obviously going to be divided by, so we have 1.36 grams of water over 1.14 grams of sodium hydroxide. So now I need to solve this for X to get that X equals to 106 multiplied by 1.36, all that divided by 14, and that gives me 7 molecules of water per each molecule of sodium hydroxide. So just to kind of sum up, I started from just my standard formula that I'm always going to use for each titration. Using that formula I was able to calculate the molarity of the base which takes part in this titration, molarity of sodium carbonate. Having molarity of sodium carbonate allowed me to find the mass of sodium carbonate that is dissolved in 1 liter of this solution. And knowing that mass, I was actually able to find out the mass of sodium carbonate which was present in 250 cubic centimeters of this solution, the amount that we made. So knowing that mass, I was able also to find out the mass of water, and that mass of water in this case was equal to 1.36 grams. Knowing mass of water and knowing mass of the substance, I was able to find the percentage of water in the substance, which was 54%. And remembering that the ratio of mass of water to mass of sodium carbonate in the sample is the same as the ratio of the relative molecular masses. So knowing that, I was able to calculate the number of water molecules per each molecule of sodium carbonate, and that was equal to 7. As always, if something's unclear, you can ask me a question either under this post, or you can send me a message on direct message on Edmodo, and I'll be more than happy to clarify any of those. And I will continue exploring volumetric analysis questions going forward. So thank you for your time and your attention, and this is Mr. Oziak out.